Okay, so here we have one type of those classic questions where two or sometimes even more boxes are connected with strings and then they're dragged across a floor or surface. And in this case, it's one of the easier versions where, first of all, the surface is frictionless, and then there are also just two boxes. Okay, so uh, these type of questions can be solved with two principles. The first principle is that the two boxes are moving at the same time, which means that they will have the same acceleration, same velocity at any instance, and the fact that the tension. And then the second principle we can use to solve these questions is that the tension on the rope is considered constant throughout. All right, so that means so for example, if we name the smaller block A and then the bigger block B, right, and then if we draw the free body diagram of the smaller box A, right, so it's gonna have the gravitational force and the or its weight, and as well as the normal force, and then it is dragged by this piece of tension, this piece of rope with a tension force on object A, so we'll call that F tension A, right? And then let's draw the free body diagram of B, right? And then this bigger block, of course, experiences weight as well as its normal force, right? And then, as explained in the question, it is there is a 75 newtons of tension force that contributes to the movement of boxes. Right? But don't forget that it is also that the B blocks is also dragging on the A block, right? And then that they have a tension B, right? But what I want to mention here is that you see that the rope between A and B, right? There A and B are connected by the same piece of rope, right? And then therefore, what we have here is the F tension on A will actually equal to F tension on B. So this piece of rope, while it is pulling on block A, it is also pulling on block B. All right. So this the tension that the same piece of rope applies on both blocks are actually the same, except that it is pulling them each blocks into different directions. All right. And then so the first thing we could do is that drawing the free body diagrams of individual blocks. Right. The second step we can do is consider this A plus B as a giant block or a giant object, a giant object. Okay, and then that is because the first principle, right? The two boxes are moving at the same time with the same acceleration and then same velocity at any given instance, right? So let's imagine these are merged or grouped together as a giant A plus B block, right? And of course, its new mass will be 25 plus 65 kilograms, which is 90 kilograms. We'll do the math later. And then it will have its weight, right? And the normal force, right? And of course, it's a frictionless surface so that we don't have to worry about any friction for now. And then the pulling force is 75 newtons. Okay, so now because this piece of rope, this piece of rope here now is considered part of the big object, right? So it's more like an internal force now. So we don't have to worry about it for this. So we don't have to worry about it for Alex， 可以不要说话吗？好吗？谢谢。And so we don't have to consider. So now because this piece of rope here is Alex. Right? So now because this piece of rope is now considered part of the A plus B giant box, it is now considered an internal force, and therefore we don't have to worry about it. All right. So now, as you can see, according to Newton's first law, right, the net force on this giant box will equal to the external, which is the only external tension force, right? Because the normal force and gravitational force will balance themselves, as you don't see the boxes moving up and down, right? That means the forces in the vertical directions are balanced, right? And then net force, according to Newton's second law, equals to mass times acceleration, right? But remember, these are Alex. 我在说话. Right. So according to Newton's second law, the net force will equal to mass of the two boxes combined multiplied by the acceleration. Okay, and then but keep in mind that this acceleration is the acceleration for A, for B individually, as well as the acceleration for A and B combined, right? So, and then we could immediately calculate the acceleration, which equals to 75 newtons divided by 90 kilograms. That will give us 0.83 meters per second square. We're going to keep two significant digits because that's what's given in the question, right? And now with this acceleration we could apply, keep in mind that this acceleration is this acceleration for box B as well as box A. And then now let's apply it back to our individual boxes, right? So if you look at box A here, its vertical forces are also balanced, and the net force on box A actually equals to the tension force, okay, which will give mass times acceleration according to Newton's second law, right? And then we have the mass of box A as well as the acceleration. Therefore, that equals 25 kilograms times 0.83 meters per second square. That equals to 21 newtons, right? And then as we said earlier, right, that the tension on the same piece of rope is considered constant throughout, and therefore the question that's asked in the force that's been asked in the question, calculate the force the second box applies on the first through tension, right? So the A box is pulling on is pulling on B box, right, through the piece of rope, right? And then with a tension force that equals to the tension force that A experiences on its own, right? And that will equal to 21 newtons.